Let's now discuss a few problems. The first problem is the following. Problem session. Problem 1. Let n be greater than 1 be a positive integer, and suppose C0 greater than C1 greater than up to Cn, which are all positive numbers, positive real numbers, be real numbers. And let P of z be defined to be C0 plus C1z plus Cnz to the power n. So we have a polynomial with real coefficients. The coefficients are special, they satisfy the condition that C0 is greater than C1 is greater than C2, so on up to Cn, all of which are positive real numbers. Then prove that there does not exist a root of P whose absolute value does not exceed 1. Let's think about what the problem says. Let's revisit the statement and see what it says. So it says that if there is a root, it does not have basically a root whose absolute value does not exceed 1. What is the meaning of absolute value does not exceed 1? Basically, absolute value is less than or equal to 1. This is what it cannot have. It does not have root which has absolute value less than or equal to 1, which means that absolute value should always be greater than 1. So rephrasing it, let me write down a solution. What do we want to show? Let me write it down in words. We want to show that if P of z0 is equal to 0 for some z0 in C, then mod z0 is greater than 1. This is precisely what we want to show. If you think about what the statement says, you want to show that there does not exist a root such that the absolute value is less than or equal to 1. So if at all there is a root, it has to be greater than 1 in absolute value. Alright, let's solve the problem. In order to do that, let's consider the polynomial which is given by 1 minus z times p of z. The reason why this is being considered is to use the hypothesis which is given here, which I am underlining in green. We are given that the coefficients satisfy a nice condition, and because of that we will be able to write this as being equal to P of z is basically C0 plus C1z plus up to Cnz to the power n minus z times P of z, which is C0 times z up to Cn z to the power n plus 1. If we have to rewrite this, this will just be equal to C0 plus C1 minus C0 times z plus Cn minus 1 Cn minus 1 times z to the power n minus Cn z to the power n plus 1. Let's just rewrite it a bit. We will be able to write this as C0 minus a polynomial of this type, C0 minus C1 times z plus Cn minus 1 minus Cn times z plus Cn times z to the power n plus 1. The reason why we rewrote the polynomial in this manner is because all these coefficients now are positive numbers. Okay, now let's consider a root. Let z0 be a complex number such that P of Z0 is equal to 0. That would imply that for Z0, 1 minus Z0 times P of Z0 is 0, and therefore C0 will just turn out to be equal to C0 minus C1 times Z plus Cn minus 1 minus Cn times Z0 times Z0 or Z0 plus to the power n, and finally Cn into Z0 to the power n plus 1. This is precisely what will happen at a root of the polynomial P. And if we are going to take the absolute value of this, it will be like this, and so this is basically absolute value of Z0 times the absolute value of C0 minus C1 plus Cn minus 1 minus Cn times Z to the power n plus Cn Z minus 1, and finally it will be like this. Absolute value of this. This is precisely what happens when you look at the absolute value of the product of two complex numbers. Remember that Z0 is a complex number, so the thing on the right is now a complex number. You can take Z0 common factor, and this is precisely what it turns out. And by the triangle inequality, we will be able to write this as absolute value of C0 minus C1 plus absolute value of C2 minus C1 times the absolute value of Z0, or maybe I should, as of now, just write it like this, plus the absolute value of all these terms individually, Cn minus 1 minus Cn times Z to the power n minus 1, plus absolute value of Cn Z to the power n, Z0 to the power n, which in particular is less than or equal to absolute value of Z0 into C0 minus C1 is just a positive number, so the absolute value will be the same, plus again similarly C2 minus C1 is a positive number. We are now using the hypothesis of the statement, which will be giving us something like this. Finally, Cn minus 1 minus Cn times mod or absolute value of Z0 to the power n minus 1 plus Cn times the absolute value of Z0 to the power n. So till now we have not assumed anything about how the root should behave. Now let us try to prove that Z0 cannot be in the closed unit disk. So if mod Z0 is less than or equal to 1, let's see what happens. Then let me just directly write this as this is less than or equal to C0 minus C1 plus C2 minus C1 plus Cn minus 1 minus Cn plus Cn. This is precisely what will happen if mod the absolute value of Z0 is less than or equal to 1. And this telescopic sum will just be equal to C0. But if you carefully observe here, we started off with absolute value of C0. Remember that C0 is a positive number. Let me write it here. C0 is the same as the absolute value of C0 because it's a positive number. So we have now a C0 here and a C0 less than or equal to at the bottom. And we know that it's equal, and therefore all these inequalities which I am now indicating, they are all equal because at the bottom it is equal. If one of them was a strict inequality, the last one would have also been a strict inequality. So all these are equal, and I am very interested in the equality which comes in what is being taken in box. So let's focus on that. Let me rewrite that below. Since the last inequality is an equality, all the inequalities above are also equalities. Therefore, we have, let me just show you once more what was put in the box. The first two of them will be equal. So let's write that down. Absolute value of z naught times the absolute value of c naught minus c1 times the z naught has been already taken care of, c2 minus c1 times z naught plus up to cn minus 1 minus cn times z naught to the power n minus 1 plus cn z naught to the power n. This is equal to the absolute value of z naught times c naught minus c1 plus the absolute value of c2 minus c1 times z naught plus absolute value of cn minus 1 minus cn times z naught to the power n minus 1 plus cn z naught to the power n. Notice that z naught can never be 0. If z naught is 0, then p of z naught is equal to 0 would imply that c naught is equal to 0, a contradiction. So z naught can never be equal to 0 because we have assumed all the coefficients to be positive. In fact, c naught is the largest coefficient. And because of that, we can cancel the absolute value of z naught because it's not 0. And what we end up is an equality in this triangle inequality. So we have hence absolute value of c0 minus c1 plus absolute plus, yeah, so I don't know whether I should be writing it down again. It's just, okay, no problem. This is cn minus 1 minus cn times z naught to the power n minus 1 plus cn z naught to the power n. This is equal to the absolute value of each of these terms separately. And so on. Let me not fill it up. And at this point, let me recall something from your course on linear algebra, which says that prove using Cauchy-Schwarz that if mod of a plus b is equal to mod of a plus mod of b, then a is equal to lambda times b for lambda in R. It's actually a straightforward check. You should sit down and prove it using Cauchy-Schwarz. Remember that we are now in a real inner product space. We are considering C as a vector space over R. So when you look at the inner product of a mod of a plus b square, if you take, that will be mod a square plus mod b square plus inner product of ab plus inner product of ba. But remember that inner product of ba, which is the conjugate of the inner product of ab here, is equal to the inner product of ab because the conjugate is equal to itself. It's a real inner product space. And you will get that 2 times the inner product of AB is equal to 2 times the product of the norm of A and B. And now you use Cauchy-Schwarz. When will there be an equality? It will be when one of them is a scalar multiplier of the other. And that's precisely what is captured here. We now have, by now, an induction argument. I will leave that for you to complete. We have that C0 minus C1 is equal to lambda times C2 minus C1 times Z naught. In fact, each of them you can write as a scalar multiple. And this is where lambda is some real number. But that implies that Z naught is equal to C0 minus C1 by lambda times C2 minus C1. Notice that lambda will not be 0. Because if lambda is 0, C0 minus C1 would be 0, thereby implying that C0 is equal to C1. So lambda can never be 0, nor will C2 minus C1 be by the very assumption. So this tells us that this is in real number. So let's go back about what happened. We have assumed that z0, the absolute value of z0 is less than or equal to 1. Then we have proved that z0 should necessarily be a real number. But we are still not through. We have to show that there is some contradiction which might come up even now, which we have to show in fact, because it cannot have absolute value less than or equal to 1. That's what we have to prove, right? Okay, so what will we do next? Notice that if z0 is greater than 0, then P of z0 is equal to c0 plus c1z naught plus something. And this is greater than or equal to c naught, because whatever is captured inside this bracket is a positive number, and this will never be equal to 0, and therefore hence z naught cannot be 0. Z naught cannot be a root. And what about if z naught is less than 0? Then let's divide the cases into two. If n is odd, what do we have? N is odd, then P of z naught will be c0 minus c1 times, okay, let z naught be equal to say minus of w or minus of a. So this is going to be c0 minus c1a plus c2a square. So let me put an a square common here, which will be c2 minus c1a, okay, c3a, I'm sorry. And n is odd tells us that final term will be of this type, a to the power n minus 1 into cn minus cn minus 1 minus cn times a. So remember, a is a positive, where a is a positive number. And each of these terms, which I am putting in bracket now, or rather I am underlining now, they are all positive. Because c0 minus c1 times a is less than 1, remember that, and c1 is less than c0. So this is going to be less than or equal to, or rather, this will be greater than, or this will be strictly greater than 0, this will be strictly greater than 0, this will be strictly greater than 0. All these terms will be greater than 0, which would imply that P of z0 is greater than 0. It cannot be a root. And what happens if n is even? If n is even, then P of z0, again we will do the same clubbing. It will be c0 minus c1a plus a square times c2 minus c3a plus a to the power n minus 2 into cn minus 2 minus cn minus 1 times a, and there will be finally one extra term, which is the last term, a to the power n times cn. It's technically minus a to the power n times cn, but I'm taking care of the minus a's powers in this manner. You should check that this has been taken care of in a correct manner. This is also again same argument tells us that this is all greater than 0. This is also greater than 0, which implies that P of z0 cannot be 0. And therefore, we have now come to a contradiction. If mod z0 is less than 0, P of z0, we have not come to a contradiction, we have just shown that P of z0 cannot be 0 if mod z0 is less than 0. If mod z0 is less than 0, we first showed that z0 should be real. If z0 is real, it cannot be a root of absolute value less than 1. So hence, we have proved that mod z0 is less than or equal to 1 implies P of z0 is not equal to 0. Okay, that completes the problem. The next problem involves the absolute value of the complex numbers. It's about how we can manipulate them to get what we want. So let me write it down, the problem. Let z and w be complex numbers such that 1 plus mod z square times w is equal to mod. And I said mod, I mean the absolute value, modulus. That's another word which is generally used. 1 plus absolute value of w square times z. This is equal. Suppose z and w are two complex numbers which satisfy this. Then either z is equal to w or zw bar is equal to 1. Let's give a quick proof of this statement. What does that inequality here tell us? It tells us that 1 plus absolute value of z square times w is equal to 1 plus the absolute value of w square times z. Recall that the product, the square of the absolute value is the norm of z, which is basically z times z bar. So rewriting this is i.e. 1 plus zz bar times w is equal to 1 plus w bar times z. Let's just rewrite it. This just can be rewritten as, oh, I made a mistake. This will be outside. Maybe I should write it here like this. W times this is z times this. Okay, so w times 1 minus, bring this to the left, this is going to be 1 minus w bar z is equal to z times 1 minus z bar w. If z is equal to 0, then what do we have? Then we have, this would imply that w is also equal to 0, and hence we have z is equal to w, and we are done. So if one of them is 0, we are through. We have that the other one is also 0, and hence they are equal. Suppose z is not equal to 0, and if z bar w is not equal to 1, if z bar w is equal to 1, again that was one of the statements which we had to prove, right? Either z bar w or zw bar. If z bar w is equal to 1, its conjugate, which is z bar w, will also be equal to 1. So this is equivalently, okay, this last part is equivalently z bar w is equal to 1. So if z bar w is not, if it is equal to 1, again we are done. If it is not equal to 1, let's see what happens. Then, in fact, let's prove exactly what is needed. If zw bar is not equal to 1, then w by z is equal to 1 minus z bar w by 1 minus w bar z. This makes sense because z is not 0 and zw bar is not equal to 1, and therefore this makes complete sense. And if we take the absolute value now, it will be the same, and this is going to be 1 minus z bar w, the absolute value of this, divided by the absolute value of 1 minus, let me write it as z w bar. But if the complex number 1 minus z bar w is what is, say, let's call it zeta, then in the denominator it's 1 minus zw bar, it is basically zeta bar. So this is just going to be equal to 1 because the denominator is the conjugate of the numerator, and the absolute value of the conjugate of a complex number is the same as the absolute value of the number. So this is equal to 1, which implies that the absolute value of w is the same as the absolute value of z, and therefore its square will also be the same, and therefore 1 plus absolute value of this is equal to the 1 absolute value of z square plus 1. and if we multiply it by this is something which we have. Hence 1 plus absolute value of w square times z is equal to 1 plus absolute value of z square times w implies z is equal to w, and we are done. The next problem deals with the notion of connectedness. We gave a characterization of connected open sets in the complex plane. We proved that an open set in the complex plane is connected if and only if any 2 points in the open set can be connected by a path. In this problem, we will specialize the result. We will show that we can actually get hold of some very special paths to join any 2 points. We will in fact show that we can get hold of a polygonal path, which I will define in a moment, such that the line segments involved in the polygonal path will be parallel to the axis, the real axis or the imaginary axis. So let me first define what a polygonal path is. A path gamma from z to w is a polygonal path if it is obtained by concatenating finitely many straight lines. If their axis z1 to z0, okay, if their axis z0 equal to z comma z1 up to zn, zn minus 1 and zn equal to w, such that, again, points in C, such that gamma is obtained by, let me write it like this, gamma z0 z1 concatenated with gamma z1 z2 concatenated with all this, and finally gamma zn minus 1 zn. Basically gamma is where gamma zi plus 1 is the straight line path which joins zi and zi plus 1. So this is going to be 1 minus s times zi plus s times zi plus 1. Notice that this is a straight line which connects zi plus 1 to zi, or rather zi to zi plus 1. So if we can get hold of finitely many paths, which, so this is in figures, it will be like this. Suppose we have 2 points. Suppose we can go like this. All these are straight lines that I am trying to draw, even if it might not look like that. This is a straight line, this is a straight line, this is a straight line, a straight line, and a straight line. So this is our z0, which is z, this is our w, this is our z1, z2, z3, z4. So in figures it will be like this. This is how a polygonal path will look like. The next problem tells us that if you have a connected set, and if you take any 2 points in the connected set, we can get hold of a polygonal path in the open set, such that each of the line segments are parallel either to the x-axis or the y-axis, the real axis or the imaginary axis. That's a special type of path we can always get in connected open sets. Let me write down the problem. Let omega contained in C be a connected open set. Then prove that, so as I was mentioning, connected open sets are special for our purposes. We can prove that given, this is actually an if and only statement, because the moment we have a polygonal path, any type of polygonal path, it's going to be a path, and we have shown that if the given domain satisfies the condition that any 2 points can be connected by a path, then it should be connected. So this is actually an if and only statement, but the forward is what needs some work. So let me just, forward direction is what needs some work. So let's prove that given z comma w in omega, there exists a polygonal path from z to w consisting of straight lines parallel to the axis, to the real or imaginary axis. Let's give a proof of this. Let's do one thing. Let's first show that in a disk we can always do this. So suppose z0 is a point in C and R be greater than 0. Then we shall first prove that the disk of radius r around z0 satisfies this condition, satisfies the above condition. Let me first give you a picture which describes what I'm going to do. In fact, I'll not write down the explicit details which I will leave for you. If this is our complex plane and if this is our point z0, suppose not, let's put it a little this way so that we can draw a big disk. Suppose this is a disk of radius r around z0. This is our z0 and this is say z. I will just prove that we can connect z to z0 by such a path. That is enough, because we could have taken 2 points and shown that the property is directly satisfied, but it's not going to be any different if we show that we can join z to z0 by such a path, because then we can concatenate the path from z0 to w, which is given similarly, and we will then get a path from z to w for some other arbitrary point w. So if we can get hold of a path like this, which is parallel to the real axis and the imaginary axis, and suppose we have a path like this, by going along this path first and then going along the second path, we get a path from z to w, right? But let's not do it that way. Let's just prove that there is a path from z0 to z, and I'll just notice the following. If z0 is equal to a0 plus b0 I. So this is basically the vector a0 comma b0, and this is just the vector a comma b, and z is equal to a plus bi. Let z prime be this point. In fact, I will not make any complicated path. It's going to be the most straightforward path we can get here, and then going this way, or rather from z0 to z, if it is like that, it will go from a0 comma b0 to, if this is a comma b, this will go to a comma b. So let z prime be the point a comma b0 rather. This is the x-axis, so a will be the same, and this is the y-axis, so it will be a comma b0. So let z prime be the point a plus b0 I. Then gamma z0 z prime, which is given by 1 minus gamma of s, given by 1 minus s times z0 plus s times z prime. This is a straight line path from z0 to z prime, and by definition this is going to be parallel to the real axis. And gamma z prime z0 of s, which is given by 1 minus s times z prime plus s times z, is a path which is, this is parallel to real axis, and this is parallel to the imaginary axis. Define gamma to be obtained by concatenating this. So I'll slowly start giving you the description of this path. You could do this inductively. That's what the theorem for finitely many paths, and that's precisely what was demanded in the theorem, right? So we can do this. From 0 to half, this will go at twice the speed. It will be gamma z0 z prime of 2s, and from half to 1, it will be gamma z prime z0 of 2s minus 1. That's precisely what the path gamma does. And gamma has segments which are parallel to the real axis. And hence we always can find, hence the property is satisfied. Oh, how did I put it here? Yes. Hence the disk dz0r satisfies the conditions, satisfies the problem. Conditions are the hypothesis of the conclusion of the problem. From here, it's the straightforward mimicking of the proof we gave for the equivalence of connectedness and there existing a path between 2 points. So define A to be all those points z in omega such that z can be joined to z naught by a polygonal path parallel to the axis. I will leave it as an exercise here because we have already done this argument once. Prove that A is both open and closed. By using the fact that disk, we just check that disk, we can do that, and by concatenating the path inside the disk, we will be able to show that it is open, and we will be able to show that its complement is open in a similar manner. A complement will be open by showing that every point will be an interior point. And with this, we will show that because z0, since z0 itself is a point in A, so we have fixed a z0 in omega before we started defining A, and because z0 is a point in A, we have A is equal to omega. We are done. So connectedness is actually kind of nice. We have some really nice paths which can be used to connect any 2 points in our given domain. The next problem deals with when a continuous map turns out to be a closed map. So again, one definition before we go into the next problem. These are some topological notions which are useful. A function f from x to y is between metric spaces. So I'm always in the world of metric spaces is said to be a closed map if f of c is closed in y whenever c is closed in x. Okay, it takes closed sets to closed sets. Image of a closed set is closed. That's not necessarily the case in a continuous mapping. You should always remember that. But if this does happen, then it's called a closed map. The problem asks us to prove that whenever we have a continuous mapping from a compact metric space to another metric space, then it should necessarily be a closed mapping. So let f from x to y be a continuous mapping from a compact metric space to another metric space. then F is a closed mapping. Okay, let's do that. Proof. Let's start with a closed subset. Let F contained in X be a closed set. We would like to show that maybe E is better. F of E is a closed set in Y. That's what we would like to show. Suppose E contained in X is a closed set. What do we know about closed subsets of a compact metric space? Since X is compact, a closed subset of a compact metric space is also compact. And now a claim, which maybe I should leave as an exercise. A continuous mapping always takes compact sets to compact sets. F of E is compact. Well, it's not difficult to check this. I will leave it as an exercise by giving you an idea. Take any open cover of F of E. When you look at let me write it down. Let U be, let U consisting of U alpha be an open cover of F of E. Remember that U alpha are all open sets in capital Y. Okay, then define, let's say, V to be collection of F inverse of U alpha, where alpha is again running over the same indexing set. And notice that this is an open cover of E. But we know that E is compact. There exist finitely many elements in the cover, which will whose union will contain E, and the corresponding U alpha i's will have the same property. So I'll just leave it as an exercise to complete the proof of claim from here. After this observation, it's quite straightforward to see that there will be a finite subcover of U as well. So the image of a compact set will always be a compact set. Now what do we know? Hence, F of E is a compact subset of Y. But we know that compact subsets of a metric space are closed. We proved that, and hence closed. Therefore, F is a closed mapping, and that completes the proof. Let's conclude this problem session by solving a very popular theorem, which is called the Hein-Borel theorem. So even though it's a popular theorem, we are going to realize it as a nice corollary to the things we have developed so far. So let me just write it down for you. Hein-Borel theorem. It gives a characterization of compact sets in Rn. So the theorem says the following: a subset K contained in Rn is compact if and only if K is closed and bounded in Rn. We didn't explicitly say what the metric is, but it's the standard metric that we will be working with. So let's prove this result. It's now actually quite straightforward for us. We have done all the preliminary work to prove this particular theorem. The forward direction is actually quite easy. Let K be compact. And we have already seen that compact subsets of a metric space will turn out to be closed. And this gives, and hence, then K is compact. Then K is closed by one of the theorems we have proved. Now let's consider the open cover which is given by all balls of radius n around 0. Notice that if you look at the union of these balls, it's going to be the entire space Rn, and hence U is an open cover of K as well. But K is compact, right? Since K is compact, U, K has an, there exists, what is this happening? There exists in such that K is contained in B01 union up to B0n, which is equal to B0n itself. And this precisely, it's a reformulation of demanding that K is bounded. And K is bounded. So if you notice, we very quickly proved that compactness immediately tells us whether it is closed, that it is closed and that it is bounded. Notice that we didn't use any specific property of Rn here. We have just used the fact that there is a metric, and that for 0 was no special. You could have taken any reference point and we would have still got this, right? It is in the converse part. So we have shown both, right? Yes, we have observed that it is closed immediately by one of the theorems we did earlier, or propositions we did earlier, and this simple observation tells us that it is bounded. Now let's assume that K is both bounded and closed. Assume that K is closed and bounded. The fact that K is bounded tells us that we can think of K is a subset of one such ball, but rather than ball, let me take something else. K is contained in A1, B1 cross AN, BN. This is a closed set. K is a closed subset of Rn, and this in particular is also a closed subset of Rn. What we will do is we will show that this kind of sets are always compact. If we show that this is a compact set, then K is a closed subset of a compact set, and hence it will be a compact set. And we'll be done, right? But showing that this is a compact set has already been done in a course on real analysis for you. It's what is popularly called as the Bolzano-Weierstrass stress theorem. I'll just show that. Well, I'll just show that this particular set is a sequentially compact set. So, in fact, I'll just show that AB is sequentially compact. We have done all the hard work to establish that the notion of compactness is equivalent to the notion of sequentially compactness in Rn. So this is sequentially compact is something which we will show. In fact, let's first show this, and then we will show that the product of the intervals, which will be a subset in Rn, will be sequentially compact. Okay, let's consider. In fact, we will. Okay, let's do this. Okay, let Xn be a sequence in R in AB. The first thing to note is that AB is bounded, and therefore we can talk about then there exists a subsequence converging to the lim sup, the supremum, converging to the supremum of A, where A is the set consisting of all elements in the sequence. I'll assume this from your real analysis course. Now, and that tells us that AB is sequentially compact, right? The moment we have any sequence, we have a subsequence which is converging to the supremum, and therefore we have a convergent subsequence. Therefore, the interval AB is sequentially compact. The next claim, so this completes the claim of this proof. Another claim now is that AB cross CD is sequentially compact, and I will leave it there after to establish for you that in Rn it will be the case. This is going to establish the result for R2. I will maybe bother about Rn, let you bother about Rn. And for doing that, let xn, yn be a sequence. Oh yes, one observation was pending here. We did have a sequence converging to the supremum. Let's call that supremum alpha. But the question always remained as to why alpha would belong to AB. The reason is because AB is a closed set. Therefore, the limit also belongs to our given set, and that is the reason why we have a convergent subsequence. If it was open AB and we were looking at the subsequence which converges to say B, if suppose the sequence xn had its supremum equal to B and we had a subsequence converging to B, it wouldn't have been of any use because B doesn't belong to our given set, right? Here the key factor is that it is closed. The supremum belongs to this closed set, and that is why it is a sequentially compact set. Now we will show that this is also sequentially compact. How do we go about doing that? Let xn1 be a sequence, be a convergent subsequence of xn. Of just the first coordinate xn. Remember that these xn's belong to closed AB, and therefore we have a convergent subsequence. Now define a new sequence. Let's call it Zn to be Zk to be equal to xnk ynk, or maybe not. Let me not bring in unnecessary notations. Let me just say that now you consider a new sequence. Consider the sequence ynk in CD. So here remember that it is with k, the indexing. Now we have just shown that CD is sequentially compact. So now there exists a further subsequence which converges in CD. And remember that the nks are obtained by considering a subsequence of xn's. Therefore, whatever subsequence you take further, that will again converge to the limit of x and k itself by going to a further subsequence yn ml or rather kl. By going to a further convergent subsequence of y and k. Let me not make life complicated. Let me just say this. We obtain a subsequence. I think we will have to write it down. Given by, let's write it down. Given by y n k l. Consider the subsequence xn kl yn kl and prove that this is converging to the limit of xn kl and the limit of yn kl, which in particular belongs to AB cross CD, and therefore we have just shown that AB cross CD is sequentially compact. That was the second claim. inductively you could argue, or you could, by an inductive argument you could show that in Rn, if you look at the product of such intervals, they will be sequentially compact. And in a metric space, sequential compactness is equivalent to compactness by induction. Hence we have A1 B1 cross AN BN is compact, and we are done. Because a closed subset of a compact set will be a compact set, and therefore K will be compact.